Auto-translation for unwritten language, translating a mostly oral language. Most speech-to-speech translation systems use text as an intermediate mode. So how do you build an automated translator for a language that has no standard written form? A new approach trained neural networks to translate a primarily oral language. Peng Zhen Chen, Kevin Tran, Yilan Yang and teammates at Meta described a system that translates speech between English and Hokkien, which is spoken by millions of people in East Asia. Few people know how to translate between English and Hokkien, which makes it hard to assemble a dataset sufficient for training an English-Hokkien translation model. However, a fair number of people can translate between Mandarin and English and between Mandarin and Hokkien. By translating from English to Mandarin and from Mandarin to Hokkien, it's possible to build a database of English-Hokkien speech pairs. The authors collected a corpus of English, Mandarin, and Hokkien data. They employed human translators to translate the corpus. They used the translated corpus to synthesize further data. The initial corpus comprised videos of Hokkien dramas with subtitles, 5.8 hours of which were manually translated from Mandarin text into English text and speech. B. An existing dataset of Hokkien speech, manually translated into English text and 4.6 hours of English speech. And C. An existing dataset of English to Mandarin speech and text, manually translated into 86 hours of Hokkien speech. To synthesize additional English to Hokkien speech pairs, the authors used an existing trained model to translate English text with matching speech into Mandarin text. Then, using the Hokkien dramas, they trained a text-to-speech transformer to translate Mandarin text to Hokkien speech. This process yielded 1,500 hours of corresponding English-Hokkien speech. They used a similar process to synthesize additional Hokkien to English speech pairs, starting with the Hokkien dramas. This process yielded 8,000 hours of corresponding Hokkien to English speech. Separate speech-to-speech systems with identical architectures translate from Hokkien to English and English to Hokkien, using Mandarin text as a stepping stone between the target languages. Given English or Hokkien speech, Hubert encoders and Hi-Fi GAN decoders learned to convert English and Hokkien speech to tokens and back. Given English or Hokkien speech, separate WAV2-VEC 2.0 transformers learned to convert them into tokens. Given English or Hokkien tokens, separate M-BART decoders learned to turn them into Mandarin or English text respectively. Given the resulting text, two transformer layers learned to translate it into Hokkien or English speech tokens. At inference, the Hi-Fi GAN decoder converts those tokens into speech. The authors compared their system to a baseline of their own design that translated directly between the spoken languages using an encoded decoder. They evaluated the systems according to R-Sir-Blue, which compares text overlap, higher is better, against reference text after translating speech to text. To render Hokkien speech as text for comparison, they developed a separate model that translated Hokkien speech into a phonetic script called Tai Lo. Converting English to Hokkien, their system achieved 7.3 R-Sir-Blue, whereas the baseline achieved 6 R-Sir-Blue. Converting Hokkien to English, their system achieved 12.5 R-Sir-Blue, whereas the baseline achieved 8.1 R-Sir-Blue. Without the augmented data, both their system and the baseline scored worse by 6 R-Sir-Blue to 9 R-Sir-Blue. Billboards are watching. AI-driven signs are deciding what to display based on data harvested from passersby. Companies that sell advertising in public spaces use face analysis and personal data to match ads with potential viewers in real time, civil liberties watchdog Big Brother UK detailed in a new report. The report compiles applications and case studies drawn from product summaries and blog posts published by ad tech companies. Quividi, a French maker of smart signs, offers a system that analyzes up to 100 faces at a time, identifying their gender, age, and mood along with the direction they're facing and how long they look at the screen. UK advertising company Ocean Outdoor uses Quivides technology in shopping malls and commercial districts in 5 UK cities. One of its ads promoted Emoji Movie by showing passersby with their faces overlaid by emojis. Another that was intended to raise awareness of suicide risk depicted a girl with a sad expression who smiled when people looked at the ad. The report compiles applications and case studies drawn from product summaries and blog posts published by ad tech companies. Quivides, a French maker of smart signs, offers a system that analyzes up to 100 faces at a time, identifying their gender, age, and mood along with the direction they're facing and how long they look at the screen. UK advertising company Ocean Outdoor uses Quivides technology in shopping malls and commercial districts in 5 UK cities. One of its ads promoted Emoji Movie by showing passersby with their faces overlaid by emojis. Another that was intended to raise awareness of suicide risk depicted a girl with a sad expression who smiled when people looked at the ad. These companies walk a tightrope over local privacy protections. AdSquare, Alfie, and Quivides tout their compliance with Europe's General Data Protection Regulation (GDPR), which protects privacy in member countries. Last year, U.S. lawmakers sent letters of concern to Lyft and Uber after some drivers independently put Alfie-equipped advertising screens in their vehicles. Both ride-share companies responded that equipment installed by drivers was beyond their control. Algorithms control the capital. A new report offers a rare peek into the use of automated decision-making tools by the government of a major city. Municipal agencies in the U.S. capital of Washington, D.C., use at least 29 algorithms to streamline their operations, according to a study by the Electronic Privacy Information Center. The authors found references to the models in public records and internal documents. In many cases, their roles were not widely known. The algorithms span a variety of municipal functions. Criminal justice. The Department of Youth and Rehabilitative Services developed a model that estimates a juvenile offender's likelihood of committing new crimes using data such as school attendance and prior court cases. The police department uses systems including ShotSpotter to locate the source of gunfire and trapwire to find patterns in reports of suspicious behavior. Economic opportunity. The Department of Human Services and Department of Employment Services score recipients of welfare and unemployment insurance on their risk of committing fraud via Fraudcaster and CaseTracker. Education. The University of the District of Columbia identifies students at risk of failing to graduate using a tool created by the Education Advisory Board, a for-profit consultancy. Health. The city's Office of Veterans Affairs developed a model that scores the risk of death for COVID-19 patients. Housing. The city's Department of Buildings scores a building's risk of code violations, based on data such as the building's age and prior history of code violations, via an algorithm developed by Georgetown University. Washington, D.C. lawmakers are considering a law that would require regular audits of decision-making algorithms used by organizations of a particular size and those that hold data on city residents. It would also enable the Office of the Attorney General and others to sue for violations. Novel views of 3D scenes. Pronto, given a number of images of the same scene, a neural network can synthesize images from novel vantage points, but it can take hours to train. A new approach cuts training time to a few minutes. Thomas Muller and colleagues at NVIDIA introduced a new method for learning representations of positions in a 3D scene. It's compatible with neural radiance fields, NeRF, a popular way to synthesize images of a scene from novel perspectives. For a given scene, NeRF learns to reproduce ground truth images shot by a camera from different positions and angles. At inference, given a camera position and angle, it generates views of a scene by sampling points along virtual light rays that extend from the camera through each pixel. Given an embedding of a point's position and the ray's direction, Separate fully connected networks compute its color and transparency. Typically many points occupy empty space, so they're fully transparent and have no color. The system combines the color and transparency of points along the ray to find the associated pixel's color. Previous efforts to speed up NERF training impose a 3D grid over the scene and learn an embedding of each grid point. When it comes to sampling coordinates along rays, these approaches interpolate embeddings of positions that fall in between the grid points. This process requires a lot of memory, and rendering is slow because ferrying data to the processor and back takes a lot of time. Limiting the total number of embeddings to fit within a process's cache eliminates this bottleneck, accelerating rendering. One way to do this is to hash the coordinates, which defines a function that maps them to the index of a list, hash table, of limited size. This makes it possible to map any number of points to a limited number of embeddings. The authors trained separate systems of vanilla neural networks to generate 20 synthetic and real scenes used in the original NERF paper. As in the original NERF and its variants, the networks learned by minimizing the difference between the ground truth images and generated images from the same viewpoints. Given a camera position and viewing angle, the system projected a ray for each pixel in the resulting image and sampled from 3 to 26 points, depending on the scene's size, along each ray. The system defined 16 3D grids with resolutions from coarse, 16x16x16, to fine, 512x512x512. Given a point along a ray at a particular resolution, it located the positions of the 8 corners of the cell closest to it and hashed the coordinates to retrieve the corresponding embeddings. Then it interpolated the embeddings to calculate a vector that represented the point. It repeated this process at each resolution, producing 16 separate hash tables. Hashing each point's coordinates at multiple resolutions kept the points differentiated by making it unlikely that different points would map to the same embedding, a phenomenon known as a hash collision, at all resolutions. The system concatenated each point's embeddings at every resolution and fed them to 2 vanilla neural networks. One network estimated opacity and the other estimated color. The authors evaluated the system using peak signal-to-noise ratio, PSNR, which measures image reconstruction quality, higher is better, and compared their results to the original NERF and similar MIP-NERF. Averaged across all scenes, the new approach achieved 31.407 PSNR after 15 seconds of training. In contrast, NERF achieved 31.005 PSNR after more than 12 hours of training, and 33.176 PSNR after 5 minutes of training, better than MIP-NERF's 33.090 PSNR after 2 to 3 hours of training.